solids are classified into three categories: conductors, insulators, and semiconductors. And we were focusing on these semiconductors. So whenever we discuss semiconductors, we always come to the concept of this idea of germanium and silicon, isn't it? Because all the semiconductor devices are basically prepared with this germanium and silicon. So these are a special class of elements which are having conductivity between insulator and conductors. Okay. So this germanium and silicon are called as single crystal or elemental semiconductors. Whereas the other than this germanium and silicon, like gallium compounds, like gallium arsenide, gallium aluminum arsenide, gallium phosphide, cadmium sulfide, all these materials are called as compound semiconductors. Okay, compound is nothing but it is a combination of different elements. Okay, so now coming to the classification of semiconductors. This is the first expected question from this unit. They may ask you, classify the semiconductors, or but 100% they'll give distinguish between intrinsic and extrinsic semiconductors. Previously, according to our previous question paper format, we can say this is a definite question in the short answer. But now, as it has been changed, we can say it is an associated question. Distinguish between intrinsic and extrinsic semiconductors, and along with that, they may give you any other question. Okay, so semiconductors are mainly two types: intrinsic and extrinsic semiconductor. So first we'll discuss about intrinsic semiconductors, and then we'll go for extrinsic semiconductors. Now, what are intrinsic semiconductors? They are pure form of semiconductors. That is, intrinsic semiconductors does not have any impurities. Okay, so at 0 degree Kelvin, it behaves as an insulator. And in these intrinsic semiconductors, energy gap is of the order of 1 electron volt. Okay, so these semiconductors, electrons and holes are solely separated by thermal excitation. Thermal excitation. Yes, yes, 57M. Can you message me? Can you message me? Any problem? If you have any doubts, please chat in this, type in this chat box. So, so semiconductors are classified into two types: intrinsic semiconductor and extrinsic semiconductor. A pure form of semiconductor is called as intrinsic semiconductor, and the energy gap of in intrinsic semiconductors will be 1 electron volt, and they behave as an insulator at 0 degree Kelvin. And by thermal excitation, the number of electrons and holes are created in these intrinsic semiconductors. Okay, so these are called as, and examples of intrinsic semiconductors are germanium and silicon. Okay, now you can see the structure of a intrinsic semiconductor. So they are tightly bound. We are taking the example of silicon, and there are no valency electrons. Clear now? Now coming to the Fermi energy. See here, the number of electrons in the conduction band will always be equals to the number of holes in the valency band. So that is why Fermi level is always exactly halfway between the intrinsic semiconductor. Okay, So here what we are doing is just we are discussing all about intrinsic semiconductor, then we'll go for the extrinsic semiconductor. So initially I'm explaining you the Fermi energy that is dependence of Fermi energy on temperature in case of intrinsic semiconductors. Okay, so what is Fermi energy? Basically, the maximum energy level occupied by a particle at 0 degree Kelvin temperature is known as Fermi energy level. So in case of these intrinsic semiconductors, Fermi level lies exactly at the middle of the forbidden energy gap between this conduction band and the valency band. Clear? So this is all about Fermi level dependence on temperature. See here. Yeah. Somebody is asking from ITA. Yeah, there is a possibility of existence of a pure semiconductor, that is germanium and silicon are the pure form of semiconductors. Okay. So by the process of crystal growth, they can be made pure, but 99% there is no chance of existence of pure semiconductors in the universe because there are some defects. Already in crystal bonding or in crystal structures, you have studied about these defects. So one or two minor defects may exist. So we cannot say exactly it is pure form. Okay, 100% pure form of germanium and silicon cannot be existed. Yes. Now coming to the next part. So this is the second expected question from this unit. The dependence of Fermi energy level on temperature. Okay. So what is the first question? Differences are distinguished between intrinsic and extrinsic semiconductor. And the second one is Fermi energy level dependence on temperature. So that is why first I'm explaining everything about intrinsic and we'll go for the extrinsic. Okay. So here, next coming to the carrier concentration in intrinsic semiconductor. What does mean by carrier concentration? It is nothing but density. Density of number of electrons and number of holes. That is nothing but, it means number of electrons in the conduction band per unit volume of the material, that is denoted by small n, and as well as number of holes in the valency band, that is denoted by always small p. Okay, so this, the presence of the number of electrons and number of holes in a conduction and valency band is denoted by concentration, that is nothing but carriers. Carriers are nothing but charge carriers, that is holes and electrons. Clear? That is denoted by carrier concentration. So now we are going to calculate how many number of electrons are present in the conduction band. Similarly, how many number of holes are presented in the valency band. But actually how these are formed? So when a suitable form of energy is supplied to a semiconductor, then electrons take transition from valency band to conduction band. Hence, the free electrons and free holes are formed in the conduction and valency band. So the formation of free electrons are known as electron hole pair generation. This definition is very important. Okay. Now in intrinsic semiconductor, always the number of electrons in the conduction band will be equal to the number of holes in the valency band. So first we'll calculate how many number of electrons are there in the conduction band. Here, more number of slides are there in this PPT because I have given you a detailed derivation of all these. That is why it took at least 10 to 15 slides for these derivations. Okay, that is here we are discussing about calculation of density of electrons. That is, Dn is the number of electrons available in energy interval E and E plus dE. So this is always denoted by Z of E, F of E, dE. What is Z of E? Z of E is nothing but a partition function. That is nothing but it explains you about density of states. That is nothing but how many number of energy states are there in the interval E and E plus dE. Similarly, F of E is nothing but probability of electron occupation. So what we need to do is you have to calculate total number of electrons. For that, you have to integrate it. How to integrate it? You have to always take from the bottom of the conduction band to go from this energy level diagram. That is from bottom of the conduction band to top of the conduction band. Always we will take the integration from this energy level to this energy level. Okay. So that is why we are mentioning like this. So integration of this. So these values are fixed. Z of E and F of E values are fixed. You need not go in depth of this. Just you have to remember the values and then substitute them because it is again a big derivation. So the derivation, we don't want to do it now. Okay, we don't have that in syllabus. Just you have to remember this value. Okay, so Z of E dE is given like this, 4 pi by h cube, 2m whole to the power of 3 by 2 and e to the power of half dE. So always we take m as the effective mass of electron, that is always denoted with a star. So me star, instead of m, we are writing it as me star. Okay. So now always it is starting from the bottom of the conduction band. So this E is taken as E minus EC, that is total energy minus bottom of the conduction band. Got it now? So therefore E minus EC is taken. Calculation of density, that is what I'm taking you. Density of energy states. Here, density of electrons is not always denoted with Dn. So first, initially, we are considering some number of electrons. What is that? That number of electrons is always denoted with Dn. Dn is equals to Z of E, F of E, dE. Got it? So how to take that number of electrons? Always we are taking them in an energy interval E and E plus dE. Clear? Because they are distributed. They are distributed within the conduction band. But we need total number of electrons. Whenever we need total number of electrons, always take the integration part. Got it now? So that is why integral of this n always gives you integral of bottom of the conduction band to top of the conduction band and this equation. And these values are fixed. That is Z of E dE is already given. And this Z of E dE, just we are manipulating. Instead of m, we are taking effective mass of electron, and instead of E, because total E we are not taking, we are taking from bottom to the top of the conduction band. That is where we are writing it as E minus EC whole to the power of half dE. Got it now? So this is the value of Z of E dE. Now coming to the F of E. What is F of E? Calculation of density of electrons is directly given. Okay, please follow it carefully. Somebody is asking me how to calculate this density of electrons. The density of electrons is given by this expression. Okay, just we are substituting the values of Z of E and F of E. This Dn already have explained you number of electrons available between the energy interval this and this. Please go through the statements and these values, this is a big derivation. Again, it is a separate derivation that we don't have in the syllabus. Directly, you have to remember this equation. Okay, if anyone wants it, you can afterwards, after the class, I'll explain you them how we got this equation. Okay, so then you have to take this and just manipulate like this. Got it? This is a equation of Z of E. And next one is probability of an electron, that is F of E. What is F of E? F of E is nothing but Fermi distribution function. Fermi distribution function is also be explained as probability of an electron occupying an energy state E. That is always given by this expression 1 by 1 plus exponential E minus EF by KT. So for all possible temperatures, this is always very much greater than KT. Then this equation reduces to exponential of EF minus E by KT. Got it? So F of E is directly written as exponential of EF minus E by KT. Now substitute this F of E value and substitute this Z of E value in the equation 1. That is N is equals to integral EC to top of the band Z of E F of E dE. Substitute these two values, okay? And a simple integration is there. Okay, simple integration is there. Just manipulating this, taking some constant outside of the integration, and then now we are getting E minus EC whole to the power of half and exponential of minus E by KT, etc. In order to solve this integral, let us assume that E minus EC is equals to X. That is, in order to solve this integration part, in the place of this, we are writing E minus EC as x. Okay. Now E minus EC as x and do this manipulation. E is equals to EC plus x, etc. Okay. Substitute that. When we substitute this entire part in terms of this x, we are getting this x to the power of half exponential minus of EC plus x by kt dx. Okay. So this x to the power of integral 0 to infinity exponential half exponential of minus x by kt is denoted as a gamma function. Okay, it is nothing but it is represented as in terms of gamma function. So the solution for this gamma function is nothing but kt to the power of 3 by 2, pi to the power of half by 2. So this also you need to remember. This also you need to remember. Okay. So this form of x to the power of half integral 0 to infinity x to the power of half exponential minus x by kt dx. This I hope you have already come across this gamma functions in mathematics. So this can be expressed as kt to the power of 3 by 2 pi to the power of half by 2. By substituting this in the equation, you are getting this expression. Okay. So this expression n is equals to 2 into 2 pi kt, 2 into 2 pi me star kt by h square whole to the power of 3 by 2 exponential of ef minus ec by kt explains you about number of electrons per unit volume of the material. Okay, it explains you about the number of electrons in the per unit volume of the material. Similarly, you have to explain about calculation of density of hole. Same thing, same equations you have to take, that is dP is equals to Z of E dE into 1 minus F of E dE. Now write what is Z of E dE and what is 1 minus F of E. Okay, so again same thing we are writing in terms of holes. Whatever we did for electrons in the conduction band, same thing we are writing in terms of holes in the valency band. Instead of M, we are writing it as mh star. And here in the case of E, we are taking EB minus E because just go through this energy band diagram. See here, you have to Yes, yeah, one of that slide I did not change actually. It is dark, so please go through it clearly after the class. Yes, sometimes why I'm discussing the entire derivation is nothing but in few, that is the last year supply and before last year regular paper, they have asked the number of carrier concentration in N-type semiconductor one time and a carrier concentration of P-type semiconductor in another time. That is why just I'm giving you the concept. Okay. So just to give this, keep it as a set. That means after preparing remaining all other topics, just go through this derivation once, understand the concept, then you can easily write it. Because if I left it completely, suppose you are going to get, if you are getting this question, you will be annoyed, isn't it? That is why just I'm explaining you one derivation so that you can follow the same for the next derivations. Okay, because I have already given you the derivations clearly in your PDF. First practice it, understand the concept, you can do it very easily because now you understood how to take the derivation. Okay, so why you remember the derivation is a mathematical path, you have to do it. Okay, how to do it? Just I'll give you the concept. First you have to take n is equals to integral z of e f of e dE. Got it? Now what is z of e? You have to write. What is f of e? Write it. Integration part you know how to do it, isn't it? You have to manipulate and all. If you post once you practice, you can easily do the mathematical part. That is very easy. You need not remember. Practice it on a paper once, definitely you'll get it. Got it? Never butify that. Clear? Don't mug up the derivation. Practice once on a paper, definitely you'll get it. If you practice with one derivation, remaining derivations you can easily do. Got it now? Yes. So now for in the case of valency band, always you have to take from like this, from this point to this point, like this you have to take. That is why we are writing in the case of this here. See here, in the case of valency band, energy of the top of the valency band. That is why EV minus E we will be taking. So in the place of E, we substitute this. In the place of M, we'll write it as mh star. Got it? Now substitute this. Yeah, that is what I'm telling. It is least important compared to all other topics in the unit. This is the least important, but even though just I'm explaining you because we got some questions in the last previous question papers. That is why if it is an associated question, unnecessarily you'll be losing 4 or 5 marks. Okay, I don't want you people to lose the marks. That is why I'm just giving you the concepts of doing the derivation. Got it? And after that, afterwards, that is up to you. You can go through this or not. Got it now? So similar things you have to substitute in this one. Okay, got it. Now substitute the same in the P and do the integration form. Again, this is in the gamma function form. You'll be getting P value. Got it now? So you got N value, you got P value. Now intrinsic carrier concentration, always N is equals to P. So the carrier concentration will be N into P. Substitute them, you'll be getting the carrier concentration value like this. Got it now? So this is Ni. This is the value of Ni. This is intrinsic carrier concentration. Got it now? So what you do is, similarly, you go for the that is extrinsic semiconductor. Got it? So based on this intrinsic carrier concentration, see, you can say the number of electrons, that is effective mass of holes, is always equals to effective mass of electrons. Got it now? So Fermi level dependence. And one thing I'll do, I'll write clearly Fermi level energy dependence on temperature. Points I'll write, diagrams, energy band diagrams I'll write and give it to you. Okay, I'll post it to you in the group. That is because, but you have to, instead of preparing with this entire derivation, but you have to be perfect with at least those 3 points because it is also very, very important question. Okay, explain the Fermi level energy dependence or Fermi energy dependence on temperature. Got it? Now coming to the extrinsic semiconductor. Okay. So in the case of valency band, Fermi distribution function always takes, that is number of holes are there, isn't it? So distribution functions according to that Maxwell-Boltzmann distribution function, some derivation part is there. There you'll be getting it as, instead of f of u, you have to take it as 1 minus f of u because you are going from down, isn't it? Top of the valency band to they are going down, isn't it? That is why always you have to take it as 1 minus f of u. Got it? Now coming to the intrinsic semiconductor. What are intrinsic semiconductor? Extrinsic semiconductor. Extrinsic semiconductors are nothing but whenever impurities are added to intrinsic semiconductor, then the resulting semiconductor is known as extrinsic semiconductor. That is, the electrical conductivity of pure germanium or silicon can be increased by adding impurities. What type of impurities are we adding? We are adding impurities of pentavalent or trivalent. That is, suitable pentavalent elements are phosphorus, arsenic, antimony, etc. Whereas suitable trivalent impurities are boron, aluminium, gallium, etc. Okay, when we add pentavalent, it becomes N-type semiconductor. When we add trivalent impurities, it becomes P-type semiconductor. Okay, so this is the structure of N-type semiconductor. Okay, and the conduction bands you can see. Always here, number of donors will be more. So this is known as when temperature increases, donor energy, that is number of electrons will get ionized and they will be accumulated like in layer, and this is known as donor energy level. Okay, it always lies exactly below the conduction band. Okay, and in case of this N-type semiconductor, Fermi energy level, what happens? Fermi level always lies near the conduction band. It has more number of electrons compared to holes. Okay, so this is the energy band diagram. So now again, similar to your previous derivation, please go through this carrier concentration derivations. I have given a detailed derivation of density of electrons in the conduction band in case of N-type semiconductor, and similarly P-type semiconductor. Please go through the derivation because already you are done with one part of the derivation. You got a concept. Same concept you apply here also. Got it? Now coming to the P-type semiconductor. So whenever a trivalent elements are added, it becomes the p-type semiconductor. In case of p-type semiconductor, Fermi level always lies near the valency band because it has more number of holes when compared to electrons. So here what is happening? In case of extrinsic semiconductor, number of holes are ionized. Okay, number of holes are ionized and they are formed as an acceptor level above the valency band. Okay, and it is always between the Fermi level as well as valency energy band. Clear, top of the valency energy band. Okay, so here temperature increases, more acceptor atoms are ionized and they are completely ionized at a particular temperature. Further increase in the temperature, Fermi level is always towards the this acceptor energy level. Got it now? So I'll write a detailed notes simply in form of intrinsic where Fermi level lies, and in case of extrinsic semiconductors, n-type semiconductor, that is relation between the Fermi level and donor, and in p-type semiconductor Fermi energy level and acceptor. Okay, so that is very, very important. Please be perfect with this topic, Fermi energy level dependence on temperature. Got it now? So this is all about basics. So what all we discussed till now, from that you'll get only two questions. First one is distinguish between intrinsic and extrinsic semiconductor. Second one is explain the Fermi energy level dependence on temperature. Okay. Now we are going to the next topics, drift and diffusion. What does mean by drift? So we were discussing about conductivities, isn't it? So if the motion of charge carriers under the influence of electric field, then we call it as drift. That means without electric field, there is no transfer of charge carriers will be taking place. Only by the application of electric field, the motion of charge carriers are taking place, then we call it as drift. Okay. So here the current density is nothing but sigma into E. So this sigma is nothing but conductivity. Okay. So the conductivity, that is J, can also be written as number of electrons into charge and Vt mu d. Okay. And that is the drift velocity that divided by E, that is applied electric field. Got it now? So we know that mobility of electrons, mu is nothing but mobility. Mobility is nothing but drift velocity by electric field. So this is all about your drift. Similarly, substitute drift velocity and all, you can write it as J drift is nothing but Ne mu Ne, and similarly Jp drift, that is whole drift, is given as P mu P E. Okay, so therefore total drift current in any semiconductor is always written as drift due to electrons plus drift due to holes. Okay, so J is equals to Jn drift plus Jp drift. Got it now? So this is all about your drift. Now coming to the diffusion, the term diffusion. So let us consider a semiconductors with charge carriers. So the motion of charge carriers due to the concentration variation is known as diffusion. That is the motion of charge carriers per unit length per unit time. See here, diffusion of charge carriers is taking place. So this delta n, that is excess of electron concentration, this rate of diffusion can be, see here, minus E into dn dou by dou x of En, or simply you can write it as E. dn is nothing but diffusion constant. E is the charge of electron and the capital Dn is diffusion constant, and dou by dou x of delta n, in the sense how many number of electrons has been transferred from one part of the semiconductor to the other part of the semiconductor is always denoted with delta n. Got it? Similarly, you go for this diffusion of holes. You can write it as negative direction because it is in the negative direction. You write it as now minus of E dp dou by dou x of delta p. Got it now? This is negatively, this is electron and this is hole. That is why we are writing like this. Got it now? So total current density due to, so diffusion also can be written as sum of electrons and holes. So what is the total current? Total current density in any semiconductor, it is always given as drift plus diffusion. Okay, Jn is equals to Jn drift plus Jn diffusion. So you can write it as like this. This is the total. So here also, in this case of drift and diffusion also, they always give you a question like distinguish between drift and diffusion. Okay, or they may ask you explain. So whenever they ask distinguish, write in a tabular column first definitions, then go for the formulas of electron and hole, and what is the total drift and what is the total diffusion. Like that 4 points you write down whenever they ask you distinguish. If not, explain what are drift and diffusion. Write only the definition. You need not go for all these things. Okay, just write only the definition and write the final formulas of drift and diffusion. That is more than enough. Got it now? Yes, all of you? So this is also an associated question, like in the sense it is also a small question. So till now, whatever the topics we have discussed, these are all for only short answer questions. That means only for 3 or 4 questions in a week. Okay, or at the most 5 marks questions only. Got it? Now coming to the next important topic. This is from here, whatever we discuss are essay type questions only. This is Hall effect. Okay, the first expected essay type question from unit 2 is Hall effect. Okay, what is Hall effect? Hall effect is nothing but just go through this diagram. When a magnetic field is applied perpendicular to a current carrying conductor, see here, this is a semiconductor, a specimen of semiconductor. So whenever the magnetic field is applied perpendicular to this current carrying semiconductor, potential difference is developed between the points on opposite side of the conductor. Suppose current is flowing in this direction. Now the opposite forces, that is opposite difference, potential difference is developed in these directions. Got it? So this effect gives information about the sign of charged carriers in the electric conductor. Got it now? So what exactly is happening is here. What exactly is happening is over here. Let us consider a semiconductor. Okay. And now here, current is passed in this direction. Now current is passed along the x direction. Okay. And a magnetic field B is established along the y direction. Okay. So then what is happening? The charge carriers are experiencing a force F which is perpendicular to this x and y, that is nothing but in the z direction. So that this direction of this force is always given by Fleming's left hand rule. If the charge carriers are electrons, they experience a force in the positive z direction. Hence, they will be accumulated on the upper surface of the specimen. See here, upper surface of the specimen, the charge carriers will be developed. Due to this fact, the upper side will be charged negatively while the lower side will be positively. And vice versa may also takes place depending upon the difference in the potential. Did you got my point? If negatively charged carriers are accumulated in the top surface of the specimen of semiconductor, then positive charge is accumulated in the bottom portion of the semiconductor. So based on this, we can identify the type of semiconductor which we are using. That is, we always consider the top portion. If it is negative, we say it is N-type semiconductor. If it is positive, we say it is a P-type semiconductor. Got it now? So from this Hall effect, we can calculate the type of semiconductor. Second one, we can calculate the conductivity of the semiconductor. Next one is carrier concentration can also be calculated by using Hall effect. And also we can calculate mobility of the charge carriers. Got it now? So these are the applications of or the uses of Hall effect. Now mathematically we'll calculate this equation for Hall effect. See here, by this what is happening? Now electric force as well as magnetic forces are there. So magnetic deflecting force is always given by Q into drift velocity into the applied magnetic field. Hall electric deflecting force is denoted by F is equals to Q into EH. So when an electric equilibrium is reached, always these two forces are equal. So equate them, okay, equate them and simplify, you'll be getting some equation. That is drift velocity is equals to J by NE. So now simplify this. This 1 by NE is always denoted with RH. RH is nothing but Hall coefficient. So you can write RH is nothing but EH by J into B. Got it now? So the ratio of electric field to the product of current density and magnetic intention in the magnetic induction is also known as Hall coefficient. So how will you define this Hall coefficient? It is the ratio between Hall electric field divided by this current density and product of current density and the magnetic induction. So this is very, very important equation. So please highlight this in the examination. So when you do this derivation, highlight this Hall coefficient and just focus this. Okay. Now coming to the next one, when Hall voltage in equilibrium, just EH is denoted by Hall voltage electric field is equals to potential per unit distance, that is Hall potential by the distance. D is nothing but here width. Here we are not considering the distance, but we are considering it as width of the specimen of the semiconductor. Okay, just substitute the values all these here in the previous equation of RH. We are getting this. Okay, so Hall voltage is equals to this. So what is our main aim? We want to obtain the value of Hall potential also or Hall voltage also. So just we are taking this. Got it now? So the main aim of this Hall voltage is, how will you write whenever you get this Hall voltage question in the examination? First write the definition, draw the diagram and explain about what is exactly happening in that and what is the use of this or the application of Hall effect by doing the derivation part. Okay, and go for the derivation part. Very, very simple manipulations are there, but your derivation should exactly show what is Hall coefficient and what is Hall voltage. Got it now? Just highlight those two and write down. Got it now? So this is all about your Hall voltage, Hall effect. Got it now? This is the very, very important one, and it is the first expected essay type question from this unit. Got it now? Now coming to the diodes part. Okay, so now by all these conductivities, now we are going to discuss about diodes. Okay, in that first we have a PN junction diode. Okay, already we have discussed this regarding this PN junction diode even in lab also. This is the symbol of PN junction diode. This is the anode one and this is the cathode. In general, it look like this. Already you have seen this in the lab. Okay, this line always explains you about the negative and this side it is the positive. Got it? Now, before that means whenever P-type and N-type are attached, that means the combination of when a P-type material is intimately joined to N-type material, a PN junction is formed. Okay, that is a piece of semiconductor diffusing P-type material to one half side and N-type material to other half side, a PN junction is formed. And a plane which is dividing these two zones is known as a junction. See here, this is a plane which is dividing exactly P-type and N-type, and this is known as a junction. Clear? So without the application of any external field, external electric field, only P and N junctions are there, then we call it as unbiased PN junction. We call it as unbiased PN junction. In that unbiased PN junction also, charge carrier will be taking place by from higher concentration to the lower concentration, that we call it as a diffusion. So by diffusion, in the unbiased PN junction also, the charge carrier transfer will be taking place. So this is the forward bias. You know very well that P is connected to positive, N is connected to negative. Okay, so then what happens? Automatically, the positive, that is light charges, will be reflected from the applied electric field and they will penetrate towards the junction, and the recombination of electron holes will be taking place. So I gave simple points over here regarding that, and formation, how it is taking place also I gave it here. Just go through this diagram and simply this is all about your forward bias. Okay. And simply, what is reverse bias? Reverse is the reverse. So that is P type is connected to negative and N type is connected to positive. Then we call it as the reverse bias. Okay. So here, this in this, they may ask you either in two ways. Explain about theory of PN junction. They may ask you, explain about theory of PN junction. When they ask theory of PN junction, please write down only unbiased PN junction, forward biased PN junction, and reverse biased PN junction. Only that part you have to write. If they ask you about this characteristics of PN junction, then you have to write about this, plot this diagram, plot this graph and explain about the characteristics. What is happening in the forward bias and what is happening in the reverse bias. Okay. In the forward bias, what is happening? Simply, whenever an electron hole combination is taking place near the junction, now covalent bond near the positive terminal if battery is breaking down and it liberates more number of electrons which enters the positive terminal so that more number of electron hole pairs are formed and a minimum voltage is required the diode to conduct exponentially. That is why see here for minimum voltage the diode is conducting exponentially and a maximum current is produced over here with majority charge carriers, combination of majority charge carriers and we call it as the forward current. So at what voltage the diode starts conducting is known as cut-in voltage or threshold voltage. That is in the case of forward bias. Now coming to the reverse bias. In the case of reverse bias, when positive terminal of battery is connected to N type and negative is connected to P type, then what is happening? Electrons and holes are attracted away from the junction. They are attracted away from the junction under action of the applied voltage and then depletion. Yes, it is an essay question only. It is an essay question only. And they may ask you in two different ways, either theory or characteristics. Okay, VI characteristics are theory. Never they ask you entire question. Clear now? So please write according to the question, answer according to the question. So if they are asking, plot this graph and explain in detail about the forward and explain in detail about the reverse. Got it now? So this is all about. So what is reverse saturation current? What is knee voltage, depletion layer, everything I gave you there. So please go through this. And because now time is going up, okay, so still we have to cover two more topics. So is it clear? Yes, any doubts in the PN junction? So this is the reverse bias. Now avalanche breakdown is taking place because the large voltage has to be applied because minority depletion width layer will be very large and all the majority charge carriers are attracted towards the junction and only the conduction here initially takes place due to the minority. So large external voltage has to be applied in order to break this so that now breakdown is taking place. So then diode starts conducting in the reverse voltage. At what voltage? In PN junction diode, somebody is asking me, that is in IT, 77 roll number is asking me, once again explain me how to write about this PN junction diode concept. PN junction diode concept is, questions are asked in two ways. One is theory of PN junction and other is VI characteristics of PN junction. In theory of PN junction, please write only regarding unbiased and biased PN junctions. Only till that part you explain. Whereas in case of VI characteristics, you have to explain, draw the forward bias circuit and explain about the forward biased characteristics and draw the reverse biased circuit and explain about reverse biased characteristics. Got it? So this is an essay type question. So please properly go through the answers. Okay. So in detail, I gave everything. Please go through the PPT. Got it now? So this is all about your PN junction diode. Got it now? Now coming to the next part of the diode, that is Zener diode. So it is a type of C. See, what is the difference between PN junction and Zener diode? PN junction, a normal PN junction diode allows electric current only in the forward biased junction. In the reverse bias, voltage is applied, PN junction, it blocks a large amount of electric current and it allows only a small amount of electric current. So for various applications, only forward biased mode is applied. That is why this is working only under forward bias. But coming to the Zener diodes are the basic building blocks of these electronic circuits. They are widely used in all kinds of electronic equipments. Okay, it works with both. In forward bias, it acts like completely your PN junction diode, but in reverse bias, it has a major application. Okay, and it is very, very important also. Clear now? So it not only works in the forward direction like a normal diode, but also works in the reverse direction. So if the voltage is larger than the breakdown voltage, then it works in the reverse bias. So that voltage is known as Zener voltage or Zener voltage. This is the symbol of Zener diode. No, sorry, this is symbolic representation. It is like other than like PN junction, it is in the Z shape. Okay. See here, this is a symbol. The arrowhead and a Zener diode symbol points out the direction of forward current, and when the diode is in the forward bias. Similarly, it is in the reverse bias. Got it now? This is the circuit diagram. Okay, this is a circuit diagram. So what is Zener breakdown? So Zener breakdown occurs in heavily doped PN junction. In the case of the Zener diode, P and N are heavily doped. And because of their narrow depletion region, they are heavily doped and reverse bias voltage is applied to the diode is increased. This narrow depletion region generates a strong electric field. So when reverse biased voltage applied to the diode reaches closer to this Zener voltage, then electric field in the depletion region is strong enough to pull the electrons from their valency band. So the valency electrons will gain sufficient energy from the strong electric field of this depletion region and will break the bonding of the parent atom. So the valence electrons will become free and carry electric current from one place to another place. So at Zener breakdown region, small increase in the voltage will rapidly increase the electric current. Got it? That is why what type of mechanism are we using in this Zener diode? We always use the Zener breakdown. So in the forward bias, it operates in the normal mode like PN junction forward bias. But coming to the reverse bias, it always uses this Zener breakdown mechanism. Got it now? Coming to the characteristics. When forward bias, it is similar to your forward bias PN junction. But when coming to reverse bias, applied to Zener, it works in a different manner. That is, when reverse biased voltage is applied, it allows only a small amount of leakage current until the voltage is less than the Zener voltage. Until the voltage is less than the Zener voltage. When the applied voltage to the Zener diode reaches the Zener voltage, it starts allowing a large amount of current. See here, it allows a large amount of current to flow. So at this point, small increase in reverse voltage will rapidly increase the electric current. Because of this sudden rise, breakdown occurs and this is called Zener breakdown. So even though here voltage is kept constant, this is a peculiar feature of Zener diode. Here voltage is kept constant. Even though current is increasing, your voltage is constant. That is why it is used for regulatory or stabilization purpose, the basic application. So because of the heavily doping concept, it is this thing is happening over here. See here, this Zener breakdown, I Z minimum to I Z maximum in this current is increasing here. Constant voltage is maintained. That is why it is used for the stabilization purpose. This is the basic application of Zener diode. Then what are the advantages of Zener diode? Because as the power dissipation capacity is very high and high accuracy, small in size, it is used for voltage stabilizers or shunt regulators, and it is also used for clipping and clamping. And remember, for all these diodes, for PN junction or Zener diode, you have to explain about first the circuit, what is it, go for the circuit diagram, then draw the characteristics. Remember, always in electronic devices, characteristics are very, very important. Promptly, so your plot should be very, very proper. That means you have to draw a proper plot and explain. Labeling should be clear and explain what is happening in the forward bias and what is happening in the reverse bias and explain them clearly, and then go for the applications of this PN junction and Zener diode. Got it now? Application. Okay. So this is the format of writing this. First, what is it? Next, go for circuit diagram, and next go for VI characteristics, and next write down the application part of the diodes. This is the proper way of writing the answer for PN junction and Zener diode. Got it now? And they may ask you very rarely distinguish between PN junction diode and Zener diode. If they ask, you should be in a position to write these points. Got it now? They may ask you like this also. So write symbols also, I did not include it. You can write the symbols of PN junction diode and Zener diode also in the differences part. Got it now? Write in a tabular column. Now coming to the last topic of this unit, that is bipolar junction transistors. Bipolar junction. Bipolar is nothing but here we are taking two PN junctions. Okay, two PN junctions we are taking. See here, two PN junctions we are taking in a different manner. Like NPN, PNP. In the sense, NP plus PN gives you the NPN junction. PN plus NP gives you the PNP junction. Got it now? So this is nothing but two junctions we are using. That is why we call it as a bipolar junction transistor. Got it now? So these are, we have three terminals here. We have emitter. This is the symbolic representation of a transistor. Okay. And these we have three parts of this bipolar junction transistor: emitter, collector, and base. So emitter is the first part, collector is the last, and base is the middle one. So emitter always supplies majority charge carriers, and base is very thin and it acts like a barrier between this emitter and collector. And the last one is collector is nothing but it always, its main function is to collect majority charge carriers through the base, and it is moderately low. Okay, so this is all about your three terminals of this transistor. Got it now? Now, important factors, what you have to remember, also I wrote it here. Okay, and please go through the important this operation of PNP and NPN transistors. So as time is up, we will discuss this part tomorrow, and then we'll go for the unit 3. Okay, so only 1 minute is there. Just so now we'll coming to the, already I gave you yesterday the question papers. So here you can see define diffusion and drift mechanism. Define diffusion and drift mechanism, and estimate concentration of electrons in the N-type semiconductor. That is why I gave you the derivation part in the PPT. Here, see here, estimate concentration of electrons in N-type semiconductor means it is a extrinsic semiconductor. Got it now? So evaluate VI characteristics of a PN junction diode. So you have to write only the second part of the PN junction diode. Got it now? So like this, please go through remaining questions also. I'll make a simplification of this. I'll tell you the topics of chapter 3 in the midst tomorrow because time is up. So I'm ending this now. Clear? Yeah, tomorrow I'll discuss everything.